Module 17b, we're going to start to really get into the nitty-gritty of things. Lots of calculations here. Now, you can get really bogged down by the math. The thing is, the math is not changing. The math is just like it was when we learned about equilibrium, and it's going to continue to be the same kind of pathway as we continue into the next chapter when we talk about just general aqueous ionic systems. But what I want you to be careful here is if you can keep track of what's happening in solution from a conceptual standpoint, you should always be able to get your math correct. So let's go ahead and walk through these objectives quick. To talk about the auto-ionization of water and Kw. We've talked about Kc or Keq. We've talked about Kp. We've talked briefly about Ka and Kb. We're going to examine Ka and Kb more in this section. But we also have Kw. Just like before, the K is the products over reactants, or this mass action kind of concept. This ratio to tell me how much of one species do I have as comparative to the other. The W, though, specifically stands for water. And water undergoes what we call an auto-ionization. And we will talk about that in this chapter. But you absolutely must have memorized this. Kw is 1.0 times 10 negative 14 at 25 degrees C. Now, most people memorize 1.0 times 10 negative 14. You'll forget the 25 degrees C. That's fine. You do need to actually know that it is valid at 25 degrees C specifically. But you do need to know this value, 1.0 times 10 to the negative 14. In fact, the entire pH scale is based on this value. You need to know the definitions of pH, pOH, and pKa. And within that, we're also going to get a concept called pKb. It's just like pKa. pKa is for acids, pKb is for bases. If you're given the hydronium or hydroxide concentration, you should be able to calculate pH, pOH, and perform the reverse operation, meaning if given pH or pOH, give me the hydronium or hydroxide concentration. Be able to calculate the pH of an aqueous solution of a strong acid or strong base, given its concentration. Calculating pHs of strong acids is the easiest calculation, comparatively speaking. Strong bases are right behind that. It takes a little more work to calculate the pH of a weak acid or weak base because they create an equilibrium. They do not completely dissociate like a strong acid or strong base does. You absolutely need to know the formula for acetic acid and recognize that it is a weak acid. Know the formula for ammonia and recognize that it is a weak base. And although I don't personally require you memorize this, you will hopefully. And although I do not specifically require you memorize this, you're going to get this from a lot of practice. You're going to see it. You're going to see it constantly. And so it's honestly easier if you just can remember. The Ka value of acetic acid is equal to 1.8 times 10 to the negative fifth. And what's convenient about that value is the Kb of ammonia is also 1.8 times 10 to the negative fifth. They represent different things. One is an acid, one is a base. But their Ka values and Kb value happen to match, so it ends up making the calculations easier. The reason I mention this, again, you're not required to memorize this. I will give you that equation for any weak acid or weak base, or that value for any weak acid or weak base. But in a lot of the homework problems you do, they're not provided, and sometimes it's hard to remember to go look it up. So if you just know the value for acetic acid and ammonia, it makes life easier. If you're given the concentration of a weak acid and the pH of the solution, you should be able to determine the Ka and pKa for the acid and vice versa. If you're given the concentration of a weak base and it's Kb, you should be able to determine the pH of the solution and vice versa. You should also be able to calculate pKb. I need you to be able to calculate the percent ionization for an acid or base if you're provided with its concentration in solution and the value of Ka or Kb. You should understand how a change in concentration affects the percent dissociation of weak acid or weak base, not only mathematically but also conceptually. Understand and correctly apply the following terms: monoprotic, diprotic, triprotic, and polyprotic. Be able to calculate the pH of a solution of a polyprotic acid. And be able to apply the simplifying approximation and check the validity of the approximation by applying the 5% rule. You guys have seen me do the 5% rule in previous examples, but this is the first time I actually just specifically introducing it and defining it. So first, let's talk about the ionization of water. What do I mean by auto-ionization? I mean that two water molecules are going to automatically react so that they're forming ions. Two water molecules come together and one of them acts as an acid and donates a proton to the other one, which acts as a base, and accepts that proton. So if this acts like an acid, This is its conjugate base. The acid donated a proton to a base. And this is my conjugate acid. You'll also see this written as H2O in equilibrium with H plus OH minus. They're both valid. It's just, remember, H plus and H3O plus are equivalent. But what we need you to know is that water is doing this all the time. Water auto-ionizes. A small amount of water molecules are constantly doing this. One water molecule is donating the proton, another one is accepting the proton. Why? Because it can. Remember, if you think about the structure of water, we know water is a polar molecule, right? We know that this oxygen has a partial negative charge. Each of these hydrogens are partial positive. We also know that water undergoes hydrogen bonding. So this hydrogen is hydrogen bonding to this oxygen. Who's to say that this oxygen doesn't say, okay, you know what, come hang out with me. This hydrogen leaves behind its electron and goes off with the other oxygen that's giving it more electron density. It happens. It auto-ionizes. This equilibrium always exists in any aqueous solution. And that's important to note because depending upon the concentration of other species in your system, this may be controlling the pH of your system. Water, therefore, is a weak electrolyte. Basically, 1 in 10 million water molecules forms ions. It's a very, very small amount, but 1 in 10 million. If you have a bottle of water next to you or a glass of water, this is happening. Remember, it's only about 18 grams of water to equal 1 mole, and 1 mole is 6.022 times 10 to the 23rd water molecules, which is, bigger amount than 10 million. So it's definitely happening in the water bottle or the glass next to you. We also have Kw. We call this the ion product of water. Again, it's set up just like we did for Ka, Kb, Kc, Kq, Kp, but in this case, the W represents the concentration of water. If you look at the dissociation of water, you've got water. Let's say we have 2 water molecules. They will form H3O plus, not putting it in I'm mixing up my reaction and my equilibrium expression. So H3O plus OH minus. I'm going to write the K expression, but I'm going to specifically use the word W for water. This would equal H3O plus concentration times OH minus concentration. Because water is a liquid, we're not going to include that in our equilibrium expression, right? So products of a reacting system, a reactant is a liquid. It's not changing overall. Only 1 in 10 million water molecules undergoes this. It's a very small amount compared to the entire amount of water liquid that's actually present. But at 25 degrees C, this value exactly equals 1 times 10 negative 14. These are in relation to each other. The concentration of hydroxide and hydronium are in relation to each other here. Basically, if I increase the concentration of hydronium, the concentration of hydroxide must decrease. If I increase the concentration of hydroxide, the concentration of hydronium must increase because this relationship is always valid. Therefore, the concentration of hydronium ion is inversely proportional to the concentration of hydroxide. So under acidic solutions, I have more hydronium ions present, less hydroxide, or more hydronium ions present, less hydroxide ions present. Under high pH, or more what we call alkaline conditions, I have more hydroxide ions present, less hydronium ions present. But they're a relationship. If I'm exactly neutral, my hydronium and hydroxide concentrations are equal to one another. Here is the pH scale. You've probably seen a scale similar to this before. I'm sure you've heard about pH throughout your entire lives. It's a big thing in the media, in consumerism, etc. They'll talk about pH adjusted water and stuff like that. Your body won't let that happen. You have Your body is the best protection you can have. So don't buy their products because they're telling you you can, alkaline water and stuff like that. Your body won't let it actually happen. It's not helping you. But what's actually happening here? We have neutral, which is a pH of 7. This is when the hydronium concentration equals the hydroxide concentration. Under acidic conditions, the hydronium concentration is greater than the hydroxide concentration. And under basic conditions, this is also known as alkaline. Alkali or alkaline are just fancy words for base, for hydroxide. And in these conditions, the hydronium concentration is less than the hydroxide concentration. And I know some students have a hard time with these symbols here, this less than or greater than signs. The way my brain sees it, the way my teacher taught it to me when I was in elementary school, she taught us to, it was really funny. She sat at the front of the room with her arms spread out really wide. And she pretended she was like an alligator. And she was like, I'm going to chomp my way to the bigger side. So whichever way its mouth is open, its facing is where it's chomping to. That's the bigger side. It wants the bigger side of the pie. So in this case, this is bigger. On this side, this is bigger. I don't know if that helps you or not, but I know students have a hard time with those. But you can kind of see some common things we have in our everyday life. So like your stomach, pH of 1. It's got to digest everything. Lemon juice, about pH of 2. Apple juice, 3. Tomato juice, 4. Black coffee, 5. Milk is actually slightly acidic, but pretty close to neutral. Pure water, pH of 7. Now, if you actually tested water straight from the tap, it's going to be a little acidic. Water easily absorbs CO2, carbon dioxide, which creates carbonic acid in solution. It's also what creates the bubbles in the drinks, and it makes the pH a little acidic. Eggs, pH of 8. Baking soda, pH of 9. Baking soda has sodium bicarbonate. Bicarbonate is a base. Hand soap. Hand soap is a little basic, so it can strip some of the oil off of your skin. Ammonia, bleach, and then concentrated solutions. So let's talk about the pH scale. These equations on this slide, you just need to know. There's just no way around it. You're going to have to memorize these. pH is defined as being equal to the negative log of the H3O plus concentration. You'll also see this written as the negative log of the H plus concentration because, again, they are inversely proportional. Hydronium and hydronium concentration and H plus concentration are identical. The OH concentration is inversely proportional to hydronium concentration, but POH is negative log of OH minus concentration. So, what's the commonality here? That lowercase p means negative log. If you can remember that, it helps on many of these. pH plus POH equals pKW, so the negative log of KW, which equals 14. Technically, 14.00. Sig figs with logs are hard, and I'll show you what I mean by that in just a minute. pKW, again, that lowercase p means negative log, so negative log of KW, which is negative log of 1.00 times 10 negative 14, equals 14.00. Now, sig figs. Technically, the way I wrote this, I would have to write 14.000. However many sig figs you have in your answer here is how many decimal places you have here. The number before the decimal place correlates to this. It is not holding your sig figs. So the number after the decimal place here correlates to the number of sig figs in your original measurement. pKa, negative log of Ka. pKb, negative log of Kb. Again, p, that lowercase p, is a way for us to represent negative log. Why are we doing this? Because some of these numbers are really small and they're hard to deal with. If we take the negative log of them, they make them manageable numbers that we can talk about and discuss and compare a little bit easier. H3O plus concentration. In order to get the H3O plus concentration, I need to undo this. To undo that, I'm going to say 10 raised to the negative pH. Hydroxide concentration, I need to undo this. To undo that, I'm going to say 10 raised to the negative POH. Again, there are tricks to remember that. You can remember that P just means lower, if you have that lowercase p, it means negative log of whatever follows. So pH, negative log of H plus concentration. POH, negative log of OH minus concentration or hydroxide concentration. pKw, negative log of Kw. You need to know Kw. Take the negative log of it, you find the value to be 14. pKa, negative log of Ka. pKb, negative log of Kb. How do I find my hydroxide concentration if I have my pH? 10 raised to the negative pH. I'm undoing that log, and then I have to do that negative sign as well. Hydroxide concentration, 10 raised to the negative POH. Otherwise, memorize. You do need to know these equations. So what is pH and pKa? And pKb kind of relates to, or does absolutely relate to this as well, but pH and pKa. pH is a measure of a proton jar fullness. Again, in the last video, I talked to you guys about this. If you didn't watch that one, this is from a girl. It's a girl. I don't actually know if she's still studying her in school, if she's got her degree at this point. Last I knew, she was getting her master's, but she goes by the Bumbling Biochemist on Twitter, and she has her own website. All of her stuff is open access, and she's got some great diagrams out there that can really explain a lot of concepts in general chemistry, organic chemistry, and biochemistry. Highly recommend checking them out. But she talks about the pH and acidity scales and basicity scales using cookie jars and Cookie Monster and how much do you want as cookies. So she says pH is a measure of a proton's jar fullness. Again, pH is the same, the inverse of 1 divided by H plus is the same as negative log. So pH equals negative log H plus concentration. So dividing by a bigger thing makes a smaller thing. So the more protons there are, the lower the pH. More acidic it is. Lower pH, more acidic. Depends on how many Cookie Monsters you start with, how many Cookie Monsters there are, and how greedy those Cookie Monsters are. How acidic is it? The more cookies, the more protons, the more acidic. The fewer cookies, fewer protons, more basic or alkaline. And again, alkaline is a measure of pH. It's telling you that it's more basic. It's got a higher pH. pKa, on the other hand, is a measure of the proton's greediness. It tells you at which pH half of the molecules of an acid are likely to be deprotonated, meaning missing their proton. If I have 100 acid molecules, at what pH will half of them have given up their proton? Why do they give up their proton? Because it's getting more and more basic in solution. On average, if you look at 2 acid molecules at different pH, if you're below their pKa, everyone has their protons. If you're at their pKa value, then one of them will have a proton, one will not. If you're above their pKa value, neither one will have protons. Why? Because at lower pH, there's more protons present. It's more protons to go around. Remember, acids are happy to give up their protons, for the most part, depending on the acid. Some are happier than others to give them up. That depends on their pKa values. How much do they want to give it up? Again, how acidic are they? Are they happy to give up their the lower that pKa value, the more okay they are with giving up their proton. So if I've got an acid that has a pKa value of 5 and an acid that has a pKa value of 2, the one that has a pKa value of 2 is more willing to give up its proton than the one that has a pKa value of 5. It's a measure of how willing is it to give up that proton. But when I'm at a lower pH, there's more protons present, So since there's an excess of protons anyway, the acids are more likely to take them. At the pKa value, it's reaching the point where half of them are going to be like, okay, you know what, I won't take a proton right now, but half of them still keep it. Past that pKa value, there's less protons present. So because there's less of them present, the acid is more, all of the acids that had that lower pKa value are willing at that point to give up their protons for the solution who otherwise needs them for something else. So different acids do have different pKa values. The higher the pKa, the greedier the molecule, meaning the more it wants its proton. And the weaker the acid, because weaker acids want to keep their protons. So let's do some calculations here. Let's look, if we're told that we have the H3O plus concentration as follows. What is the OH minus concentration, the pH, and the pOH of each system? Important to know that if you know one quantity, then you can calculate the other three values. You can do this a number of ways. The easiest for me personally is to figure out pH, then pOH, and then calculate back to OH minus, but I'm going to show you all the different ways that we can do it. So for H3O plus concentration of 10 to the minus 2, negative log of my 10 to the minus 2 concentration gives me a pH of 2. Note, it matches. It's pretty easy to do, right? If you don't have a number in front, if there's no number in front, it's implied that it's like 1.00 times, then it just matches this, and it's easy to do. You're welcome to plug this in your calculator as well. Negative log of this value, 5, 7, 8, and 13. Again, if I had a different value there, if I said 2.5 times 10 to the negative 2, it would give me a different value. I would actually have to calculate out with a calculator because I don't know that value. pOH. Well, remember that pH plus pOH equals 14. Therefore, 14 minus pH is equal to pOH. 14 minus 2, 12. 14 minus 5, 9. 14 minus 7, 7. 14 minus 8 is 6. And 14 minus 13 is 1. Now, how do I find my hydroxide concentration? Two different ways you can do this. You can remember that H3O plus concentration times OH minus concentration equals 1.00 times 10 to the negative 14. You can then solve it. You can say, okay, well, in that case, if I want OH minus concentration, 1.00 times 10 to the negative 14 divided by my H3O plus concentration will give me my hydroxide concentration. That is correct. You can also remember that your hydroxide concentration is equal to 10 raised to the negative pOH. I don't care which way you do it, but you're going to find that your hydroxide concentration is 10 to the minus 12, 10 to the minus 9, 10 to the minus 7, 10 to the minus 6, and 10 to the minus 1. And then if you hadn't found pOH yet, you could take negative log of this to get to pOH as well. And there's multiple ways you can manipulate these around, and I want you to do that. I want you to practice with that and see how do these all come together and start seeing if you can connect everything. Now, what does all this mean? What's this really telling me? Well, if the hydronium concentration is 10 to the minus 2 or 10 to the minus 5, the hydronium concentration here in both of these cases is greater than the hydroxide concentration. Don't let this mess you up. Students are going to look at these numbers. They're going to say negative 2 and negative 12. Negative 12 is bigger. No, it's not. Negative 12 is a smaller number because it's negative. So please do not let the negatives throw you off. This is acidic, and the pH will be less than 7. It's acidic because there's more H3O plus ions than OH minus ions in solution. Ten to the minus 7 and 10 to the minus 7. We see here that the H3O plus concentration equals the OH minus concentration. This is called neutral. And pH equals 7. There's an equal amount of H3O plus ions and OH minus ions in solution. And in the last case, 10 to the minus 8 hydronium and 10 to the minus 12 hydronium versus 10 to the minus 6 and 10 to the minus 1 hydroxide, we see that our hydronium concentration is less than our hydroxide concentration. This is a basic solution, which you will hear called alkaline, and the pH is greater than 7. Here, there are more hydroxide ions present than hydronium ions in solution. So in the first two, it's acidic, the pH is less than 7, because since there's more hydronium ions in hydronium ions in solution as compared to hydroxide, it controls the pH, there's more of them floating around, and it lowers the overall pH of the system. When they're equal, they cancel each other out, and at the higher pHs, there's more hydroxide present than hydronium, therefore the pH is higher. Remember what pH is. pH is the negative log of hydronium concentration. So if you ever use a pH meter to test the pH of something, it's actually looking and counting the number of hydronium ions that are present. Fewer ions, higher pH. The fewer ions that are in solution, the fewer ions get counted, the fewer ions that it registers in the system, and the higher the pH because we have less of them present. We know that we have more hydroxide than hydronium. So, what do we do with all this? Well, let's first look at our strong acids. A strong acid we know completely dissociates in aqueous solution. So this actually makes it easy for us when we're doing these calculations. They completely dissociate. So when you're doing a reaction, we write down things like HCl goes to H plus Cl minus. These are all aqueous. We use a single-headed arrow here. Because that arrow represents that complete dissociation. Why do I care? Well, when I'm figuring out the pH, it makes the math a lot easier. Let's say I have a 0.010 molar solution of HNO3, and I want to know the pH of this solution. Okay, I've got HNO3, and I've got 0.010 molar. This dissociates into H plus ions plus NO3 minus ions. It's all the same solution, which means that the molarity is comparable to the moles here, okay? So we don't even have to worry about what volume we have. I don't care if it's 100 mils, I don't care if it's a liter, I don't care if it's 5 liters, doesn't matter. We could assume 1 liter, and then we would say we have 0.010 moles. But again, it doesn't matter, we know the concentration. When this dissociates, this automatically produces 0.010 moles of H plus and 0.010 moles of NO3 minus. I don't actually have this present anymore in solution. I only have these two components. But how do I find pH? pH is the negative log of the H plus concentration. But we just determined that we have 0.010 molar H plus present. So I'm going to say negative log 0.010, which gives me a value of 2. Now, that's not quite the full correct answer. It's correct. It's not the full answer yet because we haven't figured out our sig figs yet. In this value, 0.010, I have 2 sig figs, 1 and 2. Remember, leading zeros are not significant. If you're unsure, put this into scientific notation. I have two sig figs. Because I have two sig figs, I need to say 2.00 because your sig figs are always the number after the decimal place. That 2 represents this. So 2.00 is my pH if I have a 0.010 molar HNO3 solution. How about the pH of 0.10 molar HClO4? This is also a strong acid, so I'm going to say negative log 0.10. When I calculate this out, it's going to give me 1, but I need to pay attention. I have two sig figs here, so I'm going to say 1.00. The 1 again representing the log, the 2 zeros after representing my sig figs. How about 1 molar HCl? Negative log 1.0. When I calculate that out, I get a value of 0. My answer, though, is 0.00 because I have two sig figs in that original value. pH of 10.0 molar, negative log of 10 with the decimal at the end. That decimal at the end means I have two sig figs. This is negative 1.00. Can they be negative? Yes, they can. pH can be negative. We say your pH scale is 1 to 14. That doesn't mean something can't be more acidic or more basic than 1 to 14. 1 to 14 is just based on kW. It's just a general ranking. It's a generalized scale that we use, but we can go above and below that scale. What is the pH of a 1.0 times 10 negative 9th molar HCl solution? This is actually a trick question. Why is this a trick question? Because if I have HCl, aqueous, that's going to dissociate into H plus ions and Cl minus ions, right? Like we've already discussed this. It's strong acid, it dissociates completely. Why am I giving you a trick question? I'm giving you a trick question so you don't mess this up on your own. This tells me I have 1.0 times 10 to the negative 9th molar, which means I have 1.0 times 10 to the negative 9th molar and 1.0 times 10 to the negative 9th molar. So why don't I just take this and calculate the pH? Because we have the autoionization of water. Remember, the autoionization of water means that two water molecules are always forming this equilibrium. The Kw value of this is 1.0 times 10 negative 14, which means at minimum, my H3O plus concentration is 10 to the minus 7 molar, and my hydroxide is 10 to the minus 7 molar in just a neutral solution. I always have that present. So if I have a solution that's 1 times 10 to the negative 9th molar HCl, that's adding this concentration to this already present hydronium ion. If you add 1.0 times 10 to the negative 9th to 1.0 times 10 negative 7th, it makes no difference on the system itself. That small amount dissociating because of that very, very weak HCl solution, even though it's 100%, it's strong acid, yes. Remember, strong doesn't mean that it's strong by creating a lot of protons in solution. Strong means it dissociates 100% in solution. It's such a weak concentration that it's going to make no difference whatsoever on the water itself. So water is actually stronger, and the H3O plus in solution due to the ionization of water is stronger. So the pH here will actually be equal to 7.00. Okay, so we've also talked about bases. We know that bases also dissociate 100% or completely in aqueous solution. So same kind of concept. What is the pH of a 0.01 molar KOH solution? Well, KOH is going to break apart into K plus ions and OH minus ions. If I have a 0.010 molar KOH solution, it's going to give me 0.010 molar K plus and 0.010 molar OH minus. The K plus isn't going to do anything. It's completely neutral. Why doesn't it do anything? Because K plus potassium wants to lose 1 electron, and it can be just like a noble gas. It lost that 1 electron. It has no reason to do anything to get that electron back. It's quite happy. It's hanging out as a potassium ion. It's literally just acting as an electrolyte, meaning it's helping electrons transfer in solution. That's all it's doing. It's helping keep the system neutral. But this hydroxide concentration is adding to the pH. Water itself has 10 to the negative 7th concentration for hydroxide ions in solution and 10 to the negative 7th ions, or concentration, 10 to the negative 7th molar hydronium ion concentration in solution. 0.01 molar hydroxide is much higher than the 10 to the negative 7th. So it's going to have a lot more hydroxide present than a neutral solution. So to find the pH, you can do it one of two ways. You can either remember that Kw is equal to 1.00 times 10 negative 14, and this equals H3O plus times OH minus. You can plug your OH minus into here, solve for H3O plus and solve for pH. That's fine. I don't care. Some people prefer that way. I do not prefer that way. What I prefer to do instead is find my pOH. So negative log 0.010. The negative log of 0.010 is 2.00, again, 2 sig figs, 2 decimals, and this is pOH. Now, I know that 14.00 equals pH plus pOH, so if I want pH, I've got to take 14.00 minus pOH, so 14 minus 2, I'm not going to be able to fit that, 8.00. Or I can't do math either. I'm doing well. 14 minus 2 is definitely not 8. 14 minus 2 is definitely 12. 12.00 is going to be the pH of a 0.010 molar KOH solution. What about the pH of 0.001 molar NaOH? I'm going to follow the same path. I'm going to say negative log 0. How many zeros is that? 2. 1, 2, 1, 0. It's going to give me 3.00, which is pOH, which means my pH is equal to 11. Okay, what is the pH of a 0.01 molar barium hydroxide solution? Do not let this confuse you. Do not say, oh, 0.1 molar, 0.1 molar, it's got to be 12. What is barium hydroxide? Barium hydroxide is BaOH2. In solution, it forms a barium 2 plus, I have to write it like that, plus 2 moles of OH minus. What that means is if I have 0.010 molar barium hydroxide, I form 0.010 molar barium 2 plus and 0.2 times 0.010 molar OH minus, or the equivalency of 0.020 molar hydroxide ions in solution. For every 1 dissociated, 2 form. When you take the take the negative log of that, negative log 0.02, you get 1.69897. I'm going to simplify that down. Let's see, we need 2 sig figs, so 1.70 is pOH. So 14 minus 1.70, 12.30 is my pOH. So even though it's got the same concentration as the KOH here, it's producing more hydroxide ions in solution. It's bringing it to a higher pH value. What is the pH of a solution with a pOH of 1.4? That one, just take 14 minus your pOH. 12.6. What about weak acids? How do I determine pH of weak acids and weak bases? Definitely works different. Since a weak acid only partially ionizes or dissociates in aqueous solution, it's best described as an equilibrium. So you will use equilibrium arrows here. What I have written here is HA. HA just represents a generic weak acid. specifically a monoprotic. You can use this to represent any monoprotic acid. Monoprotic means it has one proton it can lose. And this will form A minus plus H3O plus. This is your acid. Water's acting as your base. This is your conjugate base. And this is your conjugate acid. So if the reaction was flipped, A minus would accept a proton, H3O plus would donate a proton, hence the acid base. Again, HA, weak monoprotic acid, and A minus is just any -1 anion. If I was to write the Ka for the Ka expression here, I would write A minus times H3O plus divided by HA. Again, water does not factor into here because it is a liquid. It's virtually unchanged in the system. The bigger the Ka, the stronger the acid. Why? I want you to think about that question for a minute. If you have a bigger Ka, what does that mean? Bigger Ka, all Ka is doing is showing me this relationship, this ratio between product to reactant. The bigger that value of Ka, mathematically, that means that we have a bigger numerator, smaller denominator, right? Well, that means that I have more product formation and less reactant present at equilibrium. Does that make sense? Well, yeah, if we have a stronger acid, it's more willing to lose that proton. The more willing it is to lose the proton, the more product I'm going to form in solution, the more original acid molecules I don't have anymore because they've lost that proton, so therefore my reactant side will be smaller, leading to a larger Ka value. So how do I do this though? Well, let's see. Let's work this first example here, and we'll work it over on the side, then I'll erase it all and start over for the next one. I have a 0.25 molar solution of benzoic acid, and it has a pH of 2.4. I want to know what is the Ka value for this acid. It tells me the formula for benzoic acid is C6H5COOH. That should be a capital C right there. I keep forgetting to fix that. You can write that out if you would like. I don't really care. C6H5COOH plus water. All of these are going to react in water, forming equilibrium C6H5COO minus plus H3O plus. I don't like writing out all of them all the time because they take up a lot of space. This is benzoic acid. It's called benzoate. It's its conjugate base. So I tend to write HA to represent the acids because it's just faster for me. If I was to write this out, with generic terms, HA representing my benzoic acid, water in equilibrium with my benzoate plus H3O plus. I know initially I have a 0.25 molar solution of my acid, none of my conjugate base, and none of my hydronium present. Or I say approximately none, because truthfully, the hydronium concentration at the start is always equal to 10 to the minus 7th because of water. Change, minus x plus x plus x, and at equilibrium I have 0.25 minus x, x, and x. Set up my Ka expression. Ka is equal to A minus times H3O plus over HA. Plug in what we know. Well, I've got x squared divided by 0.25 minus x. I want to know that Ka value though. How am I going to find that Ka value? Well, I'm told that my pH is 2.4. If my pH is 2.4, I know that pH is equal to the negative log of the hydronium concentration. So I should be able to find my hydronium concentration. and then plug that in to find my Ka value. So my hydronium concentration is equal to 10 raised to the negative 2.40. And 10 raised to the negative 2.40 gives me 0.00398. Technically, I only have 2 sig figs here. I'm just going to keep an extra sig fig right now because I don't want to round. This equals X in my original table, right? That equals my hydronium concentration. So I can go ahead and plug that in. 0.0039, underline my sig figs, 8 quantity squared, divided by 0.25 minus 0.00398. Calculate this out, and you should get a value of 6.4 times 10 to the negative 5th. Down here it tells me it's 6.5. Looks good to me. That's basically rounding error. So we've answered the first question, 6.4 times 10 to the minus 5th. Now I'm going to erase everything, so pause the video if you need to write anything down. What about the percent ionization of 0.2 molar benzoic acid? Because I forgot to write this down here. The key to solving this question was that if you know pH, then you automatically know your hydronium concentration. And remember, these brackets mean concentration in molarity specifically. Now let's look at the next question. What is the percent ionization of 0.25 molar benzoic acid? What does percent ionization mean? Percent ionization is basically looking at how much broke apart. How much did this acid ionize? It's a part divided by whole thing. So your percent ionization equals the part ionized divided by the whole times 100%. It is equal to X from your equilibrium divided by your starting concentration times 100%. Now, I know I already erased it, but we found X to be equal to 0.00398 molar. Again, 2 sig figs. We know we initially started with 0.25 molar. Multiply that by 100%. And we see your percent ionization is 1.6%. So how much acid dissociated? 1.6% actually dissociated. Okay, what is the pH if I have a 0.05 molar benzoic acid solution? It tells me the Ka value. So instead of finding the Ka value, now I want to find the pH. Basically follow the same process that we just did. Set up your ice table. But this time we have a different concentration, 0.050 molar. It's about double. And we know our Ka equal to A minus times H3O plus divided by HA is equal to X squared 0.5050 minus X. This equals 6.5 times 10 to the minus 5th. Now, what we're going to do here is the 5% rule. I'm going to explain the 5% rule very soon, I promise, but the 5% rule simplifies the math for us. Basically, the 5% rule allows us to, anytime we have X here added to or subtracted, We're going to assume this is really, really small, that it basically goes to 0, so that we can just ignore it in our calculation. It simplifies the calculation for me. So I'm going to move over here. So it basically says now I can say 6.5 times 10 to the negative fifth is equal to x squared divided by 0.050. And you can see that that calculation is now much easier, and I do not have to solve the quadratic, which is what I just don't enjoy doing. Solve for x, and you get 0.0018 molar. And based on our table, this is equal to our H3O plus concentration, because x represents our hydronium concentration. We know pH is equal to the negative log 0.0018. Calculate that through, and you're going to get 2.74. Again, 2 decimal places because we had 2 sig figs. You can always check your answer. If you're unsure if that approximation that we made was correct, take 0.050, subtract 0.0018, and it's still approximately equal to 0.0050. So I'm going to say we're fine. I'll show you how to actually check that with the 5% rule very soon. But first, let's finish this example, or these multiple examples. What is the pH of a 0.05 molar benzoic acid solution? 2.74. Last, what is the percent ionization of 0.050 molar benzoic acid? We just talked about how to find the percent ionization. Percent ionization is your part divided by your whole. So percent ionization we know the part that dissociated, even though I just erased it. We had a concentration of 0.0018 molar that came from 0.050 molar times 100%, 3.6%. So we see we used benzoic acid both times. We got a different percent ionization. Different pHs, and different original concentrations. What does all that mean? Why are they not all the same? We have different concentrations of benzoic acid, so I guess that kind of makes sense why we have different pHs, right? But why do we have a different percent ionization? First, let me explain the 5% rule really quickly. And then I will talk about what I was just talking about with the difference in percent ionization. So, for the approximation, we call this your 5% rule. Notice the approximation in the previous example. When is it appropriate to approximate? The soft rule we can use is that we can usually approximate if your Ka value is less, or is 10 to the minus fifth or smaller. So if you have something like 1.8 times 10 to the minus fifth, you're good to go. It's a soft rule. It's not always accurate. The hard rule, we can always approximate if the concentration of acid is at least 3 times greater than the Ka value. That always holds true. If your acid concentration is at least 3 times that of your Ka, you can approximate. We call it the 5% rule. If X, meaning what you calculate, is less than 5% of what you're adding it to or taking it away from, then it's okay to approximate. So when you figure out your percent ionization, if the percent ionization is 5% or less, you're safe to approximate. So a summary from what we just saw, this illustrates an important principle. We see the percent ionization changing. The percent ionization of a weak acid or base increases as I increase that dilution. When I had a 0.25 molar benzoic acid solution, I had a pH of 2.40, percent ionization of 1.6%. But when this solution was diluted to 0.05 molar benzoic acid, my pH was 2.74 and my percent ionization is 3.6. So 0.25 is a lot bigger than 0.05, right? The 0.25 is what, 5 times bigger Yeah, that sounds right. 5 times bigger than that in concentration. The pH is lower. Makes sense, right? I've got a higher concentration of acid. The higher the concentration of acid, the lower the pH. Now, the numbers aren't massively different, but it's also a weak acid. And we're on a log scale here. Log scales make numbers look wonky when there's a change because we're dealing with really big or really small numbers. That's why we're using a log. But we're seeing a decrease in pH as I lower the concentration of the acid, but I'm also seeing an increase in the percent ionization. This is due to this dilution. As I increase the dilution, more acid can dissociate. If you think about what you've got in solution itself, you've got these molecules in solution. Your molecule with its little proton, okay? And they want to get rid of this proton, but only so many of them want to actually get rid of that proton. Some do, some don't. The more concentrated the solution, the more they see each other, the more they don't need to really get rid of that proton. The more dilute the solution, the more willing they are to get rid of that proton. It's part of the Chatelier's principle. I'm going to create more protons, more of that dissociation as I dilute that solution because there's just more possibility of them being needed in solution. What about the pH of weakly basic solutions? One key to solving problems with weak bases. Always show the reaction of weak base with water. Okay. Why do I say that? Because on acids, you don't have to. You could write HA in equilibrium with H plus A minus. It's completely valid. You could do that, and you could still set up your ice table, and you could just ignore water, and it's not going to affect you. I didn't do that in the example so far, but you could. For bases, don't do that. Always write down water. It's going to make it easier to see the process. What is the pH of a 0.75 molar solution of trimethylamine? It gives me the formula trimethylamine and then the Kb value. Trimethylamine has 3 methyl groups, so CH3, 3N. And this reacts with water to form CH3, 3NH plus aqueous plus OH minus. If I was to actually draw this out, I would have your nitrogen and your CH3 groups. That nitrogen has a lone pair. That nitrogen grabs the proton leaves its electrons on the oxygen. Giving me OH minus. So this is what's happening, and I want to know what's the pH of the system if I have a 0.75 molar solution. Well, you can use trimethylamine, and then this is trimethylammonium, just for your curiosity. When it forms the ion, it becomes the ammonium form. But like I used HA for weak acids, I like to use B for weak bases. It just makes my life easier. So B is weak base. I'm going to say my base, in this case, the trimethylamine, is going to react with water to form HB plus OH minus. This is my base, my conjugate acid. Water, in this case, acts as an acid, and this is my conjugate base. Set up your ice table. 0.75 molar. I don't have any of my conjugate acid to start, and I have approximately no hydroxide. Truthfully, I have 10 to the minus 7th molar. That's probably really small compared to what is actually going to dissociate. Minus x plus x plus x, 0.75 minus x, and x. Now I'm going to shrink this down because I don't want to erase it on you. And set up my Kb value. Why Kb? Because now I'm dealing with a base. Hb plus times OH minus over concentration of B. The other way to check it, and I forgot to mention this before, but when I write Ka, Ka, acid, has an acid in the numerator. Kb, base, has a base in its numerator. So hopefully that helps you keep track of like which one you're writing, Ka or Kb, because it does matter. And we know that the Kb value is 6.3 times 10 to the minus 5th, which is really small, probably small enough to ignore. Concentration is 0.75, definitely small enough to be able to ignore. So x squared divided by 0.75 minus x, which I'm going to simplify to x squared divided by 0.75. Solve for x. X is equal to 0.00687. We only need 2 sig figs, but I'm going to carry that 7 for right now. And what does x represent? Concentration of hydroxide. With that, I can calculate my pOH. My pOH will be equal to 2.16. I have 2 sig figs, so 2 decimal places. And I can calculate pH. 14 minus 2.16 gives me 11.84. My pH of this solution, 11.84. Okay, how can I convert between these acid-base conjugate pairs, though? I keep talking about these acid-base conjugate pairs, but I need a way to be able to correlate between them. Why? Because bottom line, sometimes we're going to calculate pH of a solution that isn't always as simple. You know, we just did benzoic acid, but what if I asked you the pH of benzoate? We did trimethylamine, but what if I gave you the solution of trimethylammonium and asked you to calculate the pH? If I gave you trimethylammonium, I would probably give you a Kb value, even though trimethylammonium itself is behaving as an acid. It can't accept another proton, but it can give one away. I need to be able to convert between the two. What we're going to find is this relationship between Ka and Kb for any acid-base conjugate pair specifically is Ka times Kb is equal to Kw. And of course, we know Kw equals 1 times 10 to the minus 14. The stronger the acid, the weaker its conjugate base. Strong acids are strong because their conjugate base is stable. It doesn't want to accept a proton. HCl forms H plus and Cl minus. Cl minus doesn't want the proton back. Strong bases want that proton. Cl minus does not. It's a weak conjugate base. It's a very stabilized conjugate base, making it a stronger acid. But let's go ahead. You do not need to know this derivation for me, but some students understand the derivation better, so let's go ahead and look at this derivation. If I look at an acid, HA plus H2O in equilibrium, this is going to form A minus and H3O plus. The Ka value here, concentration of A minus times H3O plus divided by HA. Now, what about its conjugate base? A minus is the conjugate base of HA. If I put A minus in solution, that's going to react with water, and it's going to form HA plus OH minus. This is going to be a Kb expression because hydroxide is in my numerator. So HA times OH minus over A minus. But I told you that Ka times Kb equals Kw. So let's prove it. Ka times Kb. I've got A minus times H3O plus over HA times HA over OH minus. There should be A minus in the denominator there. Should be a minus sign. Divided by A minus. A minus cancels out. HA cancels out. I am left with H3O plus concentration times OH minus concentration, which equals Kw. So the stronger the acid, the weaker its conjugate base, in the sense that that conjugate base does not want to take another proton. It's more stabilized. It's very happy being that conjugate base. It does not want to accept a proton. And that's what's making it a strong acid, the stability of that conjugate base. We also have polyprotic equilibria. Polyprotics are where you have more than one ionizable proton. We saw this with H2CO3, carbonic acid. We see this with phosphoric acid. We see this with sulfuric acid. I don't even know off the top of my head the other ones. I'm trying to think. I can't think of more. But they occur all the time. We have different ones that will do it. We have a picture here. And so polyprotic acids have more than one ionizable proton, meaning that we can pull more than one proton off. Examples include, again, like I said, sulfuric acid. Sulfuric acid is kind of a special case, but sulfuric acid, sulfurous acid, H3PO4. We can say H2A to represent a general diprotic acid, di meaning two. H3A is a generalized triprotic acid. And polyprotic just means multiple proton. So the key to understanding polyprotic equilibria, polyprotic acids donate their protons in separate successive steps, meaning they don't all come off at once, they come off at different points. Each step has its own Ka value. They're going to lose them at different pH values, and they're going to lose the first one easier than the second easier than the third. So it's harder and harder to pull off those protons. Here's a really nice chart from your book, some common polyprotic acids and ionization contents. So sulfuric acid, it is considered a strong acid. It's Ka1, meaning its first acid loss is very strong. It dissociates 100% in solution. But Ka2, that second proton does not come off that easily. Oxalic acid, we have one coming off at 6.0 times 10 negative 2 and one not coming off till 6.1 times 10 negative 5. Why do we think they're different? Well, let's think about, we can just look at, say, sulfuric acid. That should be a sulfur in the center. SO2OH. So it's a strong acid. It's immediately going to lose one proton. When it does that, it forms this. This is resonance stabilized, right? It's resonance stabilized with the other ones. But to form the second one, I need to also pull this off. Now, this compound is also resonance stabilized, but it was holding on to that proton a little bit tighter because it already took one away. So it takes more effort. I think about like a payment system to the molecule. It takes more to pay it to give it way more proton. And we can see as we continue down the chart, the difference between Ka1, Ka2, and for like citric acid, we see here Ka3, phosphoric acid, Ka3, because there are 3 we can give away. And each one is slightly different. Now, some acids are completely equivalent in their structure, some are not. And we can actually determine which acid will be lost at which point when the protons are not equivalent. Let's work an example though. Sulfurous acid, H2SO3. Step 1, we've got H2SO3 reacting with water, and in step 1, it's going to lose one proton, forming HSO3 minus plus H3O plus. Ka1, we call this Ka1 because it's the first one lost. Ka1 is equal to HSO3 minus times H3O plus divided by H2SO3. And based on the book, based on the chart, I don't know these values by heart. You would have to look them up. But 1.7 times 10 to the minus 2 is the Ka1 value. Now, step 2, H2SO3 minus can lose a second proton, forming SO3 2 minus and H3O plus. Ka2, we've got our SO3 2 minus concentration times our H3O plus concentration divided by HSO3 minus. Ka2 is 6.0 times 10 to the minus 8th. It's a lot harder to lose that second proton. That Ka value is much smaller. Remember, the larger the Ka, the easier it is to lose that proton, the stronger that acid. This one's a lot weaker. Two important principles that we note from here. Ka1 is much larger than Ka2. This is frequently true. What's always true is that Ka1 is bigger than Ka2. It's frequently true that it's much, 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 much bigger. And since Ka1 is so much bigger than Ka2, we can assume that virtually all of the hydronium ions came from the first association. So let's work an example. What is the pH, H3O plus, HSO3 minus, and SO3 2 minus concentrations in a 0.1 molar solution of H2SO3? It's a big problem. Lots of things going on. So let's work one by one. So first, we've got an H2SO3 solution. So I've got H2SO3. I'm going to react that with water and form HSO3 minus plus H3O plus. I'm told I'm starting with a 0.10 molar solution, and I have approximately no H3O plus present to start. My change, minus x plus x plus x, it's 1-to-1 ratio here. In equilibrium, I have 0.10 minus x, x, and x. Now, when I figure this out, when I write out my Ka expression, Ka is equal to the concentration of HSO3 minus times the concentration of H3O plus divided by H2SO3 x squared divided by 0.10 minus x. And my Ka for this is pretty big, so I probably cannot follow my assumption. This equals 1.7 times 10 to the minus 2. Let's try the approximation quick and check the 5% rule, but we're probably going to have to use the quadratic. I'm going to write that up here. If we try the approximation, x squared over 0.10 equals 1.7 times 10 to the minus 2. X would be equal to 0.414. And when I check that by the 5% rule, 0.0414 divided by 0.10 times 100%, I find it to be 41%. So I cannot use my approximation. I do have to use the quadratic formula for this, which I don't personally enjoy doing because I always have to remember it. But when you solve it by the quadratic, you get two x values, always. X is going to be equal to a negative 0.051, or x is going to be equal to a positive 0.034. We know negatives cannot work. It's giving us a negative just by the nature of the equation, but we know that x is equal to 0.034. Note, that means I solved one of these, 0.034 molar, because x represented the concentration of HSO3 minus. Let's continue on. Need to erase to make some space. Or at least that's the concentration of HSO3 minus right now, and I need to record that value because it's not only that, but it is currently equal to the value of H3O plus. So I guess the better place to write it is down here. 0.034 molar, 0.034 molar. Now I'm going to go through my second dissociation where HSO3 minus reacts with water to form SO3 2 minus plus OH minus. How much HSO3 minus do I have? 0.034 molar. How much SO3 2 minus do I have? None. I don't know why I just wrote hydroxide. That should definitely be hydronium. How much hydronium ion do I have? 0.034 molar from the first association. Don't forget that part. Minus x plus x plus x, 0.034 x and 0.034 minus x and plus x. Set up my Ka expression. SO3 2 minus times H3O plus divided by HSO3 minus. Remember, this is a really small number. You can get it from the previous slide, 6.0 times 10 to the minus 8th. Now, 5% rule can probably work. It's a really small value. Ka is really small. The x value is most likely going to be very small compared to 0.034. Let's go ahead and try the approximation. If I try the approximation, I get an x value of 6.0 times 10 to the minus 8th. And this is equal to the concentration of SO3 2 minus. When I check my 5% rule, 6.0 times 10 to the minus 8th divided by 0.034 times 100 gives me 1.8 times 10 to the minus 4%. We are good to go. It is a safe approximation. So we weren't able to use the 5% rule the first time. We can use it this time. But this x value tells me how much SO3 2 minus I have. So I still need to find pH. Still need to find H3O plus. Still need to find HSO3 minus. But I do know my SO3 2 minus. SO3 2 minus is 6.0 times 10 to the minus 8th molar. What about my HSO3 concentration? Well, my HSO3 is equal to 0.034 minus x. X is really, really small. X is so small, in fact, that it makes no difference, and this value stays the same. You can check it in your calculator if you would like, but 0.034 molar minus 6.0 times 10 to the negative 8th gives me a value of 0.034 molar. My H3O plus concentration is equal to 0.034 molar plus X. Again, X is so small, it makes no bearing on the calculation. And my hydronium concentration is 0.034 molar as well. And pH is equal to negative log of that hydronium concentration. So negative log 0.034. Overall gives me a pH of 1.47. So a lot of work on this calculation. But what we see is what we talked about originally, that the pH is basically controlled by the first association. The concentration of hydronium ion is controlled by the first association. The concentration of HSO3 minus remains virtually unchanged after the first association, and the concentration of SO3 2 minus is so small, infinitesimally small, it actually has no effect on our overall system.